Hi and welcome to Gaffy's Grinds. This is video 1 in our series on thermochemistry, part of our organic chemistry series. If this is your first video joining us, you're very welcome. In these videos, we take leaving cert chemistry topics, we break them down into small, manageable chunks. We try and explain them so that you really understand them, and then we'll do lots of practice questions on it. If you're wondering about the reasons as to why we do so much practice and why we break it down so small, go and watch the video, which is about how we learn. That's also on my YouTube channel if you're interested in the reasons why we do it this way. If not, just take my word for it that the way we're doing this is backed up by cognitive science on how people learn best. That's why we do the videos the way we do them. They are quite detailed, and we break things down really small, and you do loads of practice. So with that in mind, the most important piece of advice when using these videos is obviously make sure you're actually paying attention, you're listening to the explanations, and that's going to really help you understand it better. So eliminate any distractions by putting your phone in another room, closing down any other tabs you have open. And most importantly is any exercises or practice stuff that I ask you to do, it's really important that you do them and give them your full effort. Okay. Even when I ask you to do a question, do the question, put down an answer the best you can. Don't skip things, because you just don't learn anything by doing that. So if you're not going to do the practice, you're not going to give it your best shot, you're going to learn nothing doing these videos. So you're kind of wasting your time here. Okay. All right, so without any further delay, we'll get on with it. So thermochemistry, on the screen here, you're looking at 3 pictures. I'm just going to give you 10 seconds now. I actually want you to look at each of the pictures by yourselves. Okay, so what do the pictures have in common? What do they tell us? Okay, well, hopefully you figured out that they all involve chemical reactions. The first two I hope are obvious, in a burning log, and the second one is an explosion. I'm hoping at this stage in your science education, you will realize that those are definite examples of, sorry about this now, definite examples of, definite examples of chemical reactions. Okay, the third one might not have been so obvious to you. Some of you who know a bit more about how these instant ice packs work might know that they are based on a chemical reaction, but these are the instant ones, not the ones you put in the freezer. You squeeze them, there's a bag inside. Basically, you've got this outside bag, the white bag with the writing on it, and inside you've got another bag. So what's inside the bag, the small bag inside, is a liquid, and there's a powder surrounding that bag, and when you squeeze it, you burst the bag, 2 chemicals mixed together, it starts a chemical reaction. So why are these 3 in particular? Why are these 3 reactions that I've picked here? Well, they're all 3 of them are reactions that involve obvious energy changes, and that's what we're going to be talking about in thermochemistry. In particular, the word thermo, T-H-E, I'm going to write it down here, sorry. So thermochemistry. Well, we know what chemistry means, but the thermo bit refers to referring to heat energy. Okay, so heat energy is where that word comes from, thermochemistry. So we're going to be studying energy changes that happen during chemical reactions. Now, all 3 of these pictures involve energy changes happening in a chemical reaction. Obviously, the burning log releases heat to the surrounding environment. So that's why you light a fire in the sitting room. You want to warm up the environment around the log. So you burn the logs and you release heat to the sitting room. The explosion obviously releases energy as well, a lot more energy than the log. So it releases a hell of a lot of heat energy, can be felt for miles and miles and miles around an explosion. People who have been in like bomb sites or the Twin Tower explosions, for example, talked about the heat from, big, large distances away. You could feel the eyewitnesses described being able to feel the heat from streets and streets away. Okay, so a lot of energy being released in those 2 reactions. The cold pack, basically, it also involves energy transfer during the chemical reaction, and basically, whatever surface you put this against, be it your swollen arm, energy then moves from your arm into the pack. So energy is taken in by this particular chemical reaction. We'll study those a little bit more later on. Now, all of these involve obvious energy changes. They're quite clear that there's an energy change happening. But the reality is that all chemical reactions involve energy changes. They're just not always so obvious. If we just very quickly take, I'm just going to break down again, just revise ourselves. This will be familiar to a lot of us, but if we take a chemical reaction, we'll say a general chemical reaction, we'll say A plus B giving you C. Okay. First of all, quick bit of revision first. So I'm going to ask it a question, and when I ask it, I want you to speak the answer out to the screen. Okay. So which side of the arrow here, so this is the arrow showing us a chemical reaction is happening. Okay, so which side of the arrow, the left or the right, would I find the reactants? So on 3, speak your answer to the screen. 1, 2, 3. I'm hoping that you said the reactants are found over here on the left-hand side of the reaction. These are the reactants. A and B are the reactants. Okay, so on 3, what would I call C? On the right-hand side of the arrow, what would I call that? On 3, 1, 2, 3, speak your answer to the screen. You should have said C is the product. Okay, so all reactions involve basically this reactant give products. So that's the basics of any chemical reaction, just a quick revision. And if we draw just a model here to represent a chemical reaction, we'll say A is made of a molecule containing 2 of these blue atoms. And we'll say B is a molecule containing 2 of these reddish atoms like that. Okay. Now, in the beginning of the reaction, there is no product. There is no C. So there are no atoms of C just yet in the beginning of the reaction. Now, to get the reaction to start, energy is involved. Because the first thing that has to happen, if you want these things to react, is the atoms have to be free to interact with each other. Okay, so the atoms basically have to be split apart. So A has to have 2 separate atoms if it's going to react with B, which also has to be broken into 2 separate atoms. Now we call these things, what do we call the line in between the atoms here? What do we call that line here, this line? So on 3, speak your answer to the screen. 1, 2, 3. You should have said that that line is called a chemical bond. So that line is a chemical bond. Now, if we want these atoms to be free to interact with each other, then we need to break the chemical bonds. And breaking chemical bonds requires energy. So what I'm going to show here is I'm going to show an arrow which shows in the beginning, energy has to be used to break the bonds. So we say that this is, we can just call this energy in, if you like. This is energy going into the reaction. Once the bonds are broken, the atoms are free to interact with each other, and they can then react to form the product. Like this. So this, let's say, is the product. One of each. So 1 atom of A bonded to 1 atom of B, and we've got 2 of those whole molecules. Okay. Now, when the new bonds are formed, energy can then, this releases energy. So this is energy out. Okay, now what type of energy is involved here in breaking bonds and making bonds? The type of energy involved is thermal energy. And this is why we call it thermochemistry. So energy released and energy in, energy taken in, energy given out in a chemical reaction is called thermal energy. In our everyday language, we call this heat, and we have the symbol capital H. Okay, and we're going to be using that symbol quite a lot during this chapter, H. So it's an important one to take note of. Okay, so the real question is, well, overall, what happens? So overall, which is more? Overall, which is more? Is it the energy in or the energy out? Okay. So all reactions are going to involve energy in to get the reaction, to get the bonds broken at the start, and then energy out when the new bonds are formed at the end. Which one of them is bigger is going to determine what the reaction does on a whole. So looking in on from our perspective, looking in on the reaction, looking in on what's happening is going to, what really matters is which one of those amounts of energy is bigger, the energy that goes in to break the bonds or the energy that is released when new bonds are made. This will become more clearer in future video. Okay, so the next thing to discuss is where is the energy moving to and where is it moving from? What two areas is it able to move between? Well, if we briefly take a look at this little diagram here, we just want to clarify a few things. Okay, so in this first box, the first one on the left, you will see a cube box. It's like a container, we call it. It's just a box, and it's grayed out. You will see a conical flask, which is a cone-shaped flask, which is also grayed out. And inside, you can see a blue-colored liquid. Okay. The blue-colored liquid represents the material or the reaction mixture which we are studying. Okay, so this is the material. I'm just going to make the writing smaller. I'll not fit it in. Sorry. So the material / reaction mixture this is the material or the reaction mixture shown in blue here, and this is called the system. We call this the system. So the system is the material or the reaction mixture that we're studying, and it's shown in blue. It's the actual thing, the chemicals that are reacting, we call that the system. In the second box, the system is now grayed out. So the actual reacting chemicals inside the conical flask are grayed out. So this is showing us that that's separate. What you can now see in blue highlighted is the container and the area around the container. So the area around the container might be a room. It might be a basin of water if you're doing a reaction in water. It might be outside on the grass. It's the area around the container. So it's everything around the container, but does not include the actual stuff that's reacting. We call this the surroundings. The surroundings. So the surroundings is everything around the system, but not including the system. Everything around the system. Now, I just want to point out something else that could be included in the surroundings, which sometimes people forget to talk about, but it's really important. If we put a thermometer into the system to measure temperature change, which if we want to measure how energy is moving, it's going to be important to measure temperature change. So if we put a thermometer in there, that is also counts as the surroundings. It does not count as the system. So the thermometer, if we put it in there, it counts as the surroundings. So altogether, if we highlight everything, we include the system and the surroundings, we'll just write this, I suppose, as the system and the surroundings. So this is everything together, system and surroundings. Now, why is this important? Well, it's important because heat moves between, I'm going to write it as a H to show it's heat. Heat is able to move between the system and the surroundings, always. There's no container that's a perfect insulator, really. Energy will always move from one area to another. Okay, so energy is able to move between the system and the surroundings. So that is why it's important that we consider both the system and the surroundings. So sometimes heat energy will move from the system to the surroundings. Sometimes it will move from the surroundings to the system. Okay, so that we're going to be looking at that in future videos. So system and the surroundings. So all of this is really just basic background stuff, which is setting us up for future videos. Okay, so the system and the surroundings. Another important thing, I suppose, to note is that a system, say if we have a pot of boiling water. Okay, so this is a pot of boiling water and we're cooking something in here. Say we're doing a chemical reaction, we're cooking, I don't know what that is, sorry, just say a few potatoes. And as the potatoes cook in the boiling water, they're going to do chemical reactions. Now, I have two options. So I'm going to draw a second saucepan with water, and I've got potatoes in here as well. Same system. The system is obviously potatoes in the water inside the container. That's the system, the potatoes and the water. The surroundings is obviously the saucepan and the area, say your kitchen, around the saucepan. But I've got two options. In one of them, I can put a lid. Okay, so in one of them, I can put a lid. Now, in red, what I'm going to show here is I'm going to show the energy. So energy is able to move freely from the system to the surroundings, energy. But in this one, energy is also able to move from the system to the surroundings because the lid is not going to stop energy from moving. There's no material out there that's perfectly able to stop energy from moving. So energy will always pass. If you feel a saucepan, whether the lid is on or not, if you touch the sides of a saucepan, it's going to feel hot. You're going to be aware that energy is moving out of the saucepan. So energy is always going to be able to move through the saucepan. Okay. But in the first example, it's not just energy that can exit the saucepan or that can transfer out of the saucepan. I'm going to show in purple here, matter can also transfer out of the system. Water as steam can transfer out of the system. Okay. Matter can transfer out of the system. And also, condensed water vapor could also flow back down into the system because the lid is off. So condensed water vapor from the air, from the surroundings, can flow back into the saucepan. This is what we call an open system. Open systems allow energy and matter to be transferred between the system and the surroundings. But a closed system, like is shown over here, a closed system, this is a closed system because energy can leave, can transfer between the system and the surroundings, but matter cannot because the lid prevents matter from moving from the saucepan to the surroundings and from the surroundings back to the saucepan. So open system and closed system. Now, one thing not to do here is not to mix up. A closed system is not one that stops energy moving. Okay, that is a common mistake we would make here because the word closed, it makes it sound like nothing can move. Energy can always move. Energy can always be transferred from the surroundings to the environment, from the system to the surroundings. Okay, but matter cannot always be. It depends if a lid is on or a lid is off, if the container is sealed or if the container is not sealed. That's what it depends on, whether matter can move or not. Okay. So here's just a quick summary of some of that. Oh, sorry. I suppose the one more thing I suppose we need to talk about is this word delta, this letter delta that we're going to see. We're going to see this phrase delta H. Delta with the triangle is the Greek symbol delta. And the Greek symbol delta we use to refer to a change. So delta H refers to a change in heat because it's delta, which means change. H is heat, change in heat. So when we're talking about delta H, what we're really talking about is how has the heat changed in the system? Heat change in the system. And heat changes in the system can be negative numbers or positive numbers. So if the delta H is negative for a system, that means the system has lost heat. Now, where did heat go? Remember, the heat, people say the word lost. I don't really like that word, lost. Heat is lost, is what you will hear when the delta H is negative. Obviously, if it's negative, it means there's less of it, right? It means that it's gone, so it's not there anymore. But heat is lost or heat is destroyed is not a great way of saying it, because it makes it sound like it's gone or that it doesn't exist anymore. And just like we had in previous lessons, we had the law of conservation of mass, where we said matter cannot be created or destroyed. It only gets changed from one form to another. Well, for your junior cycle, we would have also learned about the law of conservation of energy, which is basically the exact same thing, except you put the word energy instead of mass. Energy cannot be created or destroyed. It just changes or moves from one place or one store to another, just transfers basically. So a better word to use here instead of lost or destroyed is energy is transferred. So the heat change in the system, if it's negative, it means it's not in the system anymore, but it didn't get destroyed. It must have got transferred. Now, remember over here, where's the options? Where does it transfer between? Well, we already learned that it transfers between the system and the surroundings. So if delta H is negative, that means the system doesn't have the energy anymore. The energy has been transferred to the surroundings. If delta H is positive, that means there's more energy in there than there was in the reactants. So basically, we're talking about the energy change between the reactant and the products. When the reaction happened, is there more energy there now than there was at the start? If there is, energy must have been taken in from the surroundings. If there's less energy was given out to the surroundings. Okay, we're going to do a couple of questions now, guys. Okay, so like I say, it's really important that you give these your absolute best shot. Okay, I'm hoping you won't have too many problems with them. I always try and make sure the questions are directly related to what the video has been about. So you shouldn't need any to go and watch anything else or extra help. Now you might need some basic knowledge, which I'm hoping this isn't the first topic you're doing in chemistry. I'm hoping, you know, what we've done here is building on other stuff that you've done already. So what I want you to do is I want you to pause the video now, and in your copy, wherever you're doing your revision questions, your practice questions, I want you to pause the video and try these questions now, please. Okay, so you should only be watching the video now if you have tried to do all of these questions to the best of your ability. Okay, so the answers are going to be coming up now. Okay, I'm hoping then that you have managed to do these. Okay. And I will just throw up the answers here. Oh, yeah, okay. So question 1 here. It said, identify the system and the surroundings for these in question 1. So the system in question 1 was the solution of chloropropane and KOH. Those are obviously the reactant chemicals of solution of 1 chloropropane, and KOH was the reactant chemicals. The surroundings, well, it was in a beaker in a lab. So the surroundings are the beaker and lab. Okay, so well done if you got that right. Okay, I'm hoping that you did. If you didn't, and you're not sure, you can't think of what the difference between system and surroundings is, I will go back and watch that bit of the video again. Okay, so what about vaporized crude oil in a fractionating column? So hoping that you have already watched our lessons on fuels and you know what crude oil is and you know what a fractionating column is. So the vaporized crude oil is the system, and the surroundings is the fractionating column, and obviously the air or the surroundings outside the fractionating column as well. So inside the column is the system, and then the column itself, and the outside is the surroundings. Melting ice in a cup, the system is the ice, and the surroundings is cup and the air around the cup. I'm presuming there's air around the cup. The cup could be in water, then it would be the water around the cup, whatever is outside of the cup. So the cup and the outside of the cup. Greenhouse containing photosynthesizing plants. So a little link to your biology here. Well, the photosynthesizing plants are the system, and the surroundings is the greenhouse, and the air are outside the greenhouse. Okay, I'm hoping that's pretty straightforward. Basically, whatever's reacting is the system, and the rest is the surroundings. Right, second question, identify what type of systems the following environments are, either open or closed. So the ocean was open. Bottled water was closed if the lid is sealed and open if the lid is not sealed. So I'm hoping maybe I need to make that question a little bit clearer. It doesn't say it's sealed bottled water, so maybe I should put that in for the future. Closed if the lid is sealed, open if the lid is not sealed. Conical flask in a titration, well, that would be an open system. There's no lid on it. An aquarium is an open system. Most aquariums, anyway, that I know of, don't have a lid that is sealed. Okay, certainly be open for feeding them, and a lot of aquariums, even the big aquariums that you can go walk into with the big massive tanks, they would all be open at the top for divers to get in, to put food in and stuff like that. So that is an open system. And a boiling pot with a lid on, that would be a closed system. So again, if you're getting these right, that tells me you understand them. You really have understood the stuff. So that's what we're looking for. A little bit deeper now. So in question 3 says, explain your answer to question 2A. So here is a good answer here. 2A was about the ocean. The ocean is an open system because both energy and matter can be exchanged between the system and the environment. There's no lid on the ocean, basically. So that lets matter flow freely between the atmosphere and the water. So it can go up and down. Water can evaporate, water can condense, other gases can dissolve and dissolve into the water and then evaporate away from the water. So it's certainly an open system because both matter and energy can be transferred. Number 4 says, explain your answer to 2E. This was the boiling pot with a lid on it. So a boiling pot with a lid on is a closed system because energy can be transferred to the surroundings, but matter can't be transferred. So that's why it's a closed system. So I'm hoping that you did that, you wrote that, especially paying attention to the fact that a closed system can release or can transfer energy, but cannot transfer matter. That's really important to have in your answer. Okay, last one, and I'm going to help you write this now because it's good if I modeled how to write these kind of answers. So critique the statements. The statement, the reactants lost energy. How could the statement be changed to make it more specific? So again, the word that we don't really like here is this word lost. Okay, and that's probably the weakness in that statement. So the reactants lost energy. So now, if you weren't able to write an answer for that, now that I've pointed that out for you, the lost bit, is there any way that you could pause the video now and improve or try and improve that answer there now? So pause the video and do that if you haven't already. Okay, so we're just going to write an answer here, question 5. So question 5. So how could we improve it? Well, instead of saying the reactants lost energy, we would say energy was transferred from the reactants to the surroundings. Okay, so that would be a much better way of saying the reactants lost energy. Energy was transferred from the reactants to the surroundings. So it wasn't lost, it didn't just magically disappear and not to exist again. It went somewhere. Okay, so let's be specific. Where does it go? It transfers from the reactants to the surroundings. All right, that's it for today. It was just a short video, really to get us started and give us some key vocabulary that we're going to need to help us build up to future videos. If you want to take a few notes there, I'm just going to end the video. You can pause this last table if you want to make a note of a few of those key words, because we are going to use those words in the future, and it's important that you kind of have an automatic understanding of what I'm talking about when if I say H or delta thermal energy, or if I talk about a system and the surroundings, it is important that you know what those things mean. So if you want to make a note of those and maybe just kind of have a look over them and use maybe cover and basically check, do you know them? So write them down, then cover them over, check, do you know what each one means? And then take your hands away, have a look then to see if you're getting them right. That's the best way to try and learn them. Okay, so I'll see you in the next video on thermochemistry.